All right, good morning, everyone. How are y'all doing? Good. So we had our first exam. We still have 2 students that need to take the exam that had some things come up. So can't go into details about the actual problems yet, but I can, for the students that took the exam, I can talk about the grades. 4 A's, 5 B's, 3 C's, 1 D, 3 F's. These are the actual grades for each student. Green is an A, orangish is B, yellow C, red F. Okay, or red or D is an F. The class average on the exam was a 74.4, standard deviation of 23 points, meaning there was a pretty big spread of the grades, as you can see, all the way from 15 to 100. So we had a huge standard deviation. Historically speaking, and I didn't go back and look at every class I've taught Cal 2, but looked at like the past 2 semesters, and the class average on the first test over the last 2 years is right around a 76, 77. But I wouldn't feel bad about that as a class, because those classes, I always gave them a review, like an actual, here are some problems, go do a review. I think you all did very, very well on the exam, considering all I did was told you like the types of things to be prepared for. So I think given that, I was pleased with what I saw. And then I guess the bad news is that historically, looking back, 61.8, 62 is the average on the second exam. So that just gives you some indication of that the second exam is going to be harder than this first one was. That doesn't mean that y'all have to get a 62 average, okay? That means just you need to work hard and be ready, all right? Okay, any comments or questions or anything about that? You should have gotten your grade. You should be able to see your test that I graded in Canvas and see where I marked off. If you haven't done that, you can go do that.
Sir, I did have a question.
Yes.
For our next test, will we get a review, or will it be the same with just?
I think I will. Here's the thing. If I give you a review, I don't want you to expect the solutions to the review. Okay, does that sound fair?
Yeah,
I'm willing to give you a set of problems to do, to practice, to kind of help you kind of gauge what you're going to see. But in terms of getting the solutions, you're going to need to visit me during office hours if you want to check to make sure you did something right. And the reason for that is because you're at home doing this on Zoom, and I'm trying to make this fair. If I put the solutions out there, that's just a very, very easy document to cheat off of, because you've got the solutions that I provided you. It's too, I just don't feel good about it. So yeah, okay. All right. So that's the first order of business, is that we are going to finish integration by parts. We did not do a couple of examples. We're going to start 6.2, which is called trig integrals. Trig 6.2 is broken into 2 main ideas: trig integrals, and then the second part is trig substitution. So next time we meet, hopefully, if we can get through everything, we'll get to trig substitution next time. I just feel a little bit like we're not going to get through all of the trig integrals today. We'll see. I don't think we will. All right. What's due this week? Is there any handwritten? Let me just check this real quick to see, because I might have to change this. First part only was due the 6th, the 13th, 6.1. Second part, yeah, okay, so that's good. Let me see what the calendar says here. Yeah, okay, yeah, so we're okay. 6.1 is due on, so the second part of 6.1 is due for Super Bowl Sunday. All right. The next order of business is completely, has nothing to do with this class. I just wanted to kind of talk to you all about something. So I don't want to take up more than 5 minutes here. So over my past 20 years of teaching, I've always been very much into working out. I did try a lot of triathlons, things like that when I was younger. I injured myself about 1.5 years ago, and up to then, every year I would just like start getting into, I do a lot of cycling, riding my bike and stuff like that. I used to actually used to live out in Bull Verde, and I taught at UTSA and at Northwest Vista. So I would, from Bull Verde, I'd ride my bike to UTSA. I'd teach a class in the morning at 7 a.m. and then I'd ride to Northwest Vista and I'd teach classes, and then I'd ride home. So it was a 74-mile loop that I would do, and I would do that 3 days a week. So I was like doing over 200 miles a week on my bike. So I was very, very fit. Right now, I'm officially in like the worst shape of my life because that injury, I've not been able to get back into it, but I've healed to the point where I can start riding again. And so I'm going to start being very healthy and eat right and pay attention to track what I'm eating and track my bike rides and everything else. So my goal is, I have a pretty low goal. I should be able to do this, is to lose 12 pounds in 12 weeks. So by the end of the semester, lose 12 pounds. It's very much within reason, barring an injury. If I reach that goal, everybody gets 5 points on the final. Okay. So that should motivate you to motivate me. All right. Like, and I've told all my classes this, all right, so that everyone's on me now, like, hey, did you work, are you keeping track? What did you eat this weekend, right? So, and I'm doing this because I want to be accountable, right? And so maybe you can make a goal for yourself. I'm not talking about exercise or just like, make a goal to do better, study harder, do something, right? I'm trying something for myself to better myself. So maybe you can try something as well, right? Now, I'm also going to, this I've never done in all my years of teaching. Give me like 2 or 3 weeks to get my cardio back up. Right now, it's pathetic, but it takes me about a couple of weeks. I'll get my cardio back up, and I'll actually be open to anyone who's interested in riding with me on the Leon Creek Greenway. If you're familiar with that, that's the trail I ride. So, I made my schedule this semester so that on Monday, Wednesday, after this class, after our office hours, I'm going to the trail. So if anyone's interested in joining me, I'd be open to that idea, because then, more people you have like, hey, let's go, let's do this. It makes that sort of thing much, much easier. So, okay, we good? That took less than 5 minutes.
Sir, I have questions.
Yes. Yes.
What area are you located by?
Well, I usually drop in. The 2 places I like to drop in for that trail are Military and 410, and then I also can drop in off of Grissom, and there's 2 trailheads over there. There's the Cathedral Rock, and then there's another one. I try not to go all the way to like OP Schnaple, and there's also a drop in over by UTSA near the Jury Inn. I could do that one too, the Jury Inn. It's just a little further for me.
What day did you say again?
Monday, Wednesday, for sure Monday, Wednesday, because it's going to be in the afternoon. The weather should be okay. Tuesday, Thursday, it's mornings. Like I'm talking like 7:45 a.m. But I'm not sure the weather's there yet. I won't ride. If it's below 52 degrees, I won't ride. It's just too cold. So,
Do you only do cardio with your bike, or also by just,
I do all my riding is for my cardio, and then at home I'll do some other stuff. I have a rower and just like some other weights and stuff, free weight stuff, just light stuff. So I'm just talking about riding. So
riding, okay,
yeah.
Dang, because I don't know how to ride a bike, but I have really good resistance.
Do you have a bike?
Cardio.
Do you have a bike? I can slow you. I won't run because my knees are bad, and running just beats my knees up. So it's all like.
Okay.
Okay, we'll talk more about it later. Let me get my cardio back up. Okay, right now I had trouble doing an hour the other day, and I did it very slow. It was like 12 miles an hour. It's pathetic, but I'll get there. Okay, let's finish up integration by parts. So we had the test on it, but there were a few problems that we had not seen how to do, and they weren't on the test. So here's one. We did something similar to this when we did, like, I think we did arc sine or arc tangent, but here's an integral natural log of x dx. We're trying to find the antiderivative of natural log of x. And really, I know the derivative of natural log, right? Derivative of natural log is 1 over x, but the antiderivative I don't know. So what I'm going to do here with integration by parts is I'm going to choose my u and my dv. And I'm going to choose the u to be the natural log of x, and then the dv to be the dx. There was one like this on the test, right? But it was, I can't talk about it anymore. Never mind, sorry. I'm not sure if the students who haven't taken it are here. I think maybe not. Okay. All right, so that's what I'm going to choose. Now I'm going to just complete the table. So I take derivative here. So du equals 1 over x dx. And then v here would be x, because the antiderivative of 1 dx is x. And now I just apply the formula, right? Ultraviolet minus the integral of voodoo. Ultraviolet minus integral of voodoo. And so this will become ultraviolet, which is the natural log x times x minus the integral of the v times the du. And what's real nice here is that this x and 1 over x will cancel out. You just get a 1 there. Now I'm going to rewrite the front one. I'm going to put the x in front of the natural log. And now I've got a real nice integral, antiderivative of 1, which is just x, and then add my constant of integration. And that's it. So the antiderivative of the natural log of x is x natural log x minus x. That's the antiderivative. On the test, I saw some people put natural, they did integration by parts on a problem, and they did dv is natural log x, and then they said v is 1 over x, which is not the case, right? This is not right. So this is us actually, now we actually do know what the antiderivative of natural log of x is. All right. Questions there?
No, but I can see all of my errors on the test right there.
Right there, yeah.
Yeah, and that I was multiplying the top half by the integral.
Yeah. Did you get my note on I think you had applied the formula wrong, or I think you were missing the minus in there or something?
Yeah.
Okay. Okay, so now on this one, the integral of e to the square root of x dx, I give you a hint here that you're going to make a u substitution first. Okay, now that I'm giving you this hint, but you have to imagine that during the test, you wouldn't be given this hint. So when we look at this here, it doesn't seem like integration by parts is going to work right away. It doesn't seem that like that's the case. But if I make a u substitution first, so basic u substitution is not integration by parts. I'm going to let u be the square root of x. And just watch what happens. The derivative of this is 1 over root x dx. And so this does not look like it's right, because the substitution technique is you're supposed to find your u, which I found. So I'm going to call that square root of x u. But I'm supposed to see its derivative somewhere. And right now, I don't see this derivative. I don't see 1 over root x anywhere. So I'm thinking, okay, this isn't going to work. However, if I continue with this, I can multiply both sides by the root of x, which again, we didn't really ever do that before, because We don't want u's and x's mixed together. In our new integral, we should just have u's, not x's. But here, if I multiply both sides by root x, I'm going to have u's and x's mixed together, except for the fact that I know that the square root of x is u, so I can replace that with u. That's the key here. This can become u du is dx. And now you can rewrite the integral. So this integral becomes e raised to the square root of x, which we call u, times dx, but dx we just determined, dx here we just determined is u du. So I can multiply this by u du. And now I'm just going to rewrite this. This is just integral u e to the u du. So that's where we are. Any questions? We're not done, but any questions on us getting that? I made a substitution, and this is where I am now. This I can do with integration by parts. This I can do. Now, there's a little bit of a little subtle problem, though. In our integration by parts formula, we have uv minus integral v du, right? And we were supposed to do this table with a u and a dv here, and then go fill out the table. The problem is that I'm already using u in the original integral. So if I'm going to do integration by parts, right, I can't use those letters because I'm already using u. So I've got to do something different like this. Maybe I'll use, I can use anything. How about I use w over here and dv here? And then use the same format. I have to choose a w, which in this case, I'm going to let it be u, because when I take the derivative of it in the new integral, it'll go away. And then over here, this will be e to the u du, which I can integrate. Does that make sense, y'all? No? Okay. Questions?
So it's kind of, we're introducing new, like u's as a w. Would it be like kind of like a second step to it?
Well, look, when we first learn integration by parts, we have an integral and then we have some functions of x in here. And so we come over here and we use u and dv, and we pick one of these, you know, one of these goes here, the other one goes here. But the point is that this has x's, the original integral has x's. So when we use u and v in our formula, you know, we could have used anything. We could have used any letters we wanted, right? U, v, w, q, it doesn't matter. It just can't be x because x is already being used. So if I'm going to do integration by parts on this, right, I can't use u because I'm already.
So we can use any letter pretty much.
What's that?
We can use any letter pretty much.
Letter,
We're just
yeah.
choosing w.
I just chose
So it
w.
doesn't be u. Okay.
So it's not you, exactly. All right, so here I go. I'm gonna complete the table. All right, so the derivative of w is du, is a or 1 du if you want. Okay, and then over here, the antiderivative of e to the u is itself. So we integrate to go up, we differentiate to go down, right? And now you can't use ultraviolet minus voodoo anymore, right? You can't use those letters. That's why I think it's more important to understand that the formula, you first multiply those two together. So that will be the u times e to the u, then minus the integral. And now the integral is going to be the diagonals multiplied together, which is e to the u times 1 du, which is just e to the u du. And I know the antiderivative of that. The antiderivative of e to the u is itself plus c. And then we have one more step. We have to replace u with what it was, and earlier u was square root of x. So we are there. Square root of x, e to the square root of x minus e to the square root of x plus c. There it is. if we differentiate that, we should get back the original integral, right? What's in the integrand. I don't think I feel like doing it, but are there questions? Making a U substitution first, which didn't seem very natural, but it works. All right, last one. Creating a reduction formula. So let me preface this problem with this. This example that I'm about to show you is not necessarily something that I want you to be able to do. All right, like I don't expect that you do this on a test. What I want you to see is how we can use integration by parts to create formulas. All right, to create formulas. So let me go to your formula sheets. Let me see if I can find this. Hold on. Where is it? It's not here. Darn it. So in the textbook, in the back of the textbook, there are a bunch of sheets, a bunch of pages in the back. I provide you in your Canvas page, I provide you the first 6 reference sheets from the back of the book. But there are actually, page 6, there's 7, there's 8, 9, 10, there's actually 10 reference sheets. And the last ones, 7, 8, 9, and 10, are all formulas for doing integrals. Like if you see a certain type of integral, here's the formula for it. So in here, there is one particular formula that I want to show you where it comes from. So here's the formula. Okay, so if we go to the back of the book, this is actually, this is reference page 9. It's formula number 73. And here's the formula they have. Integral sine raised to the n of u equals -1/n, can't read, sine to the n-1 of u cosine u plus n-1/n integral sine to the n-2 of u du. Okay, that is the formula they have. All right. So here's what I'm going to do. First thing I'm going to do is show you how you could use this formula. And the second thing I'm going to do is I'm going to show you where the formula comes from. All right, I'm going to actually generate that formula. But let's just see how we use it first. Okay, I want to just show you why it would be useful to have. Okay, here we go. So what if we needed to do the integral of sine to the 3rd power of x? Let's use x instead of u. All right. Well, according to this formula, that means the n here would be 3, right? N would be 3. And so all I'd have to do is plug 3 in for all the n's. So this would just become -1/3 sine to the, okay, 3 minus 1 is 2, so sine squared x, I have to use x because my original integral is x, cosine of x, moving on, plus, now n was 3, right? So 3 minus 1 is 2, so I put 2/n, which is 3, and now integral, so I still have to do an integral. Do y'all see that? I still have to do an integral, but now this new integral is sine to what power?
The first.
The first power. So it's just sine x dx, right? And do you see that sine x dx, like we know the antiderivative of that, right? So this becomes -1/3 sine squared x cosine x plus 2/3. Okay, the antiderivative of sine is negative cosine. So negative cosine x plus c. There's my antiderivative. Why? Because somebody gave me a formula, right? So there you go. You with me? There was no work to be done other than apply the formula. So what if we had this now? What if we had a different problem? Let's go sine to the 5th power x dx. Well, we would do the same thing, right? Use the formula. It'd become -1 over 5 sine to the 4th x cosine x, right? So I'm just using the formula again, replacing all the ends with 5. So 1 over 5 inverse sine, or -1 over 5 sine to the 4th power of x cosine x plus 4/5 integral sine to what power?
Third.
Third x dx, right? Now, so in order to do sine to the 5th power, I'm going to have to be able to do sine cubed, right? But hey, this is that, right? Which is this. So in other words, if I was, let's say we never did this up here. Let's say we never did that. What I would do is first use the formula to get this to sine to the 3rd. And then I'd use the formula on the sine to the 3rd to get it down to the sine to the 1st. So it'd be like 2 steps. Does that make sense? It'd be big and messy, but that's the way you do it. And if this was sine to the 7th, you would first use it to get to sine to the 5th, then use the sine to the 5th to get to sine to the 3rd, and then use the sine to the 3rd to get to sine to the 1st. And what you're doing is you're reducing the power each time you use the formula. That's why they call it a reduction formula. Kind of makes sense? Mohammed, question?
And if it was like an even number, it would just be 1 at the end, I guess.
Yes, if it was well, yes, it would be sine to the 0,
Yeah.
right? Power, which would just be 1.
Yeah.
Exactly.
Okay.
Okay. That's the formula. It's nice, right? And there's like hundreds of formulas, right? There's hundreds of formulas. This used to be the way engineers did it. There used to be like entire, like compiled formulas for integrals that were like entire textbooks thick of different types of antiderivatives. And engineers would be like, oh shit, I need to do this integral. Let me go to this reference and see if I can find it in here. And they, there it is. There it is. I'll just use this formula, right? That's the way it used to be. And then computers came along, and now, you know, the technology has gotten to the point where you just go to like Wolfram Alpha or Symbol Lab or something and type it in, and there you go. It does it, right? So it's kind of obsolete. These formulas are kind of obsolete, but it's important to know that they came from somewhere. All right. So let me now show you where the formula comes from. Okay. I'm going to show you where the formula comes from. And that means I'm going to start from scratch and I'm going to turn it into this. You ready? So let's say we're trying to do sine to the nth power. Let's do x. Let's do x dx. And just remember that what I'm going to try and do right now is show you this formula is true. Just replace all the u's with x's. All right. If I can do that, hopefully you'll be convinced. You ready? Okay. Hold on a second. I'm having a brain fart. I forgot how to do it. Okay, I think I just remembered. All right, you ready? This is the way it's done. First step is to rewrite this as integral sine to the n-2x times sine squared x dx. Oh, hold on. 1, oops, 1, n-1, sine. Okay, so all I'm doing here is just basically using properties of exponents, right? If I have x to the nth power, that's the same as x to the n-1 times x to the first power. Because you would add these powers together and you would just get x to the n. Y'all agree with that? I'm just doing the same thing with sine. So I split it into 2 little pieces here, which is kind of very odd, but that allows me now to do integration by parts, to have 2 different pieces. And the first piece I'm going to pick is U, and the second piece is dv. The way I'm going to pick it is I'm going to pick dv to be sine x dx, right? Which is the second part over here. That's my dv. And I picked that because I know how to integrate it. And then my u is going to be sine to the n minus 1 of x. Let's start with the integration. If I do this and go up and get v, the antiderivative of that is negative cosine x. Y'all follow? Negative cosine x, antiderivative of sine. This derivative is not as easy as it may look. I'm going to need some room. Du is, okay, so remember, this is sine to a power, right? Sine to a power. So the first thing I have to do is bring the power out front, right? Like, think about it. If I asked you to do sine cubed x, take the derivative, you would go 3 sine squared x times cosine x. It would be chain rule, right? 3 comes out, then change it to a 2, and then take derivative of sine and get cosine. Same idea, except my power is n minus 1. So I have n minus 1 comes out. I have sine to what power?
N minus 2.
N minus 2, because I have to take 1 power away from that, of x. Chain rule times cosine x dx. So here's where we are. This is equal to ultraviolet, which are these two multiplied together. So negative cosine x, let me do it this way. Negative sine to the n minus 1 of x cosine x. That's these two multiplied. Put the negative out front. Minus the integral voodoo, right? Voodoo. So I have negative cosine x times n minus 1 sine to the n minus 2 of x cosine x dx. So do y'all see that's just basically me making first this very clever move. Like, this here to here is not a natural move, but once I did that, do y'all follow how I'm just doing integration by parts now? Yes. Okay, let's keep going. First thing I'm going to do here, I'm going to take this negative sign out here and make this a plus. So this is going to become negative sine to the n minus 1 x cosine x plus integral. Now, wait, you know what? Let's take the n minus 1 out. The n minus 1 is a constant. Y'all see that? This n minus 1 is just some number. Let's just pull it out of the integral. And then I'll have sine to the n minus 2 of x. And then I had 2 cosines here being multiplied. So cosine squared x dx. That's where we are right now, right? That's where we are. The next move, because we can't do anything with this in terms of, like, this isn't just like a basic U sub or anything like that. Integration by parts on this again is going to be no good, okay? Because you can't let the cosine squared be the dv. It's you're not going to be able to integrate it. So we're kind of stuck here until I realize this next thing. I'm going to cheat and copy and paste. Good. So here's the next thing I'm going to do. I'm going to rewrite this cosine squared x using a Pythagorean identity. I'm going to rewrite it as 1 minus sine squared x dx. That's the same thing, right?
Quick
It's the exact
interruption,
same
sir.
thing. Pardden
Really
me?
quickly. Quick
Yes, thank-
interruption, sir. Sorry
Yeah,
about
yeah.
that.
No, it's
I wanted
okay.
to ask, is this the type of math we're going to be finishing in the end of the semester, where we're going to be like
No.
these moving pieces? Okay, cool.
No, this is just to show you that these formulas that you see in the back of the book are generated by humans. Like, it's not like we found some scroll somewhere behind a bush and it had all the formulas for math. You know what I'm saying? Like, some alien being didn't give us all this. Like, we had to figure this shit out. So this is an example of me showing you how to figure out a particular formula. And it's like, once you see it, it's like, okay, yeah, that's not, I mean, yeah, it's hard, but it's not like crazy. It's doable.
It's not incomprehensible.
Exactly, exactly. And it makes you feel like, some things that may appear very, very much to be impossible are within grasp. All right. You just have to be willing to try. And, somebody tried this first move, right? This first move right here. Somebody figured that out to do that first, and that was a pretty big leap of thinking. And now that you've seen it, like, yeah, it's not that big of a deal, but someone had to figure that out. And that's the way math works. Like if you're like a math major, you start to see that, like, this is the way math is. It's like these weird leaps of thinking. And it's like, once you do those leaps, you're like, oh, okay, it's not so bad. It's the actual leap is the hard thing. Okay, so I did this. Now the question is, why did I do this? Well, watch. If I distribute this through the parentheses, let's talk about what we get. Cheat again. So what will happen here is that when this thing hits the 1, it's itself, right? So I have itself there. There it is. And then when I hit this one, I'm going to have minus, right? Because it's a minus. Now look at it. It's sine to the n minus 2 of x times sine squared of x. You can add the exponents, can't you? What's n minus 2 plus 2?
N.
Sine to the n, right? So this is just sine to the n of x, and then all of this dx, right? Okay, still doesn't look like we've done anything, but let me keep going. What I'm going to do next is something that I think you'll agree is allowed. I'm going to split this into 2 integrals. So I'm going to make it this first integral minus this other one as a separate integral. And I'm allowed to do this because we already know that when it comes to integrals, if you have 2 terms, right, separated here, 2 terms separated with subtraction, you can take the antiderivative of each one separately, which is exactly what I'm going to do. I'm going to do each one of these separately. Questions? Here's the big part, okay? Remember, what we're looking at, everything we see here, what we're saying this is this original problem, right? This original problem is equal to this, right? So the original problem was this, right? That was the original problem. And we're saying it's equal to this. Does anyone see what I'm gonna do next? Who sees it?
It's at the end again.
Say again?
It's at the end again, so you're just gonna write it out again, I guess, for that.
When you
end
say it's at
portion.
the end again, you see it over here again, don't you?
Yes, yes.
Integral, and you see it over here. And here it's being subtracted. Oh, you know what I didn't do this big
Okay.
mistake? Hold on. Do y'all see that n minus 1? That n minus 1 is acting on everything here. I forgot to put it here. Please put an n minus 1 there because it acts on both integrals. Okay, so I see it here, I see it here. So here's what I'm doing. I'm going to add n minus 1 of these integrals to both sides. Do y'all remember the rabbit out of the hat problem that I did in class? I called it the rabbit out of the hat problem. We did this in the rabbit out of the hat problem. What we were looking for appeared on both sides of the equation. So the reason I'm doing that is because it'll go away over here, won't it? It's gone. And over here, what will we have? Let's see. How many of these integrals do we have? One of them here, right? We have one of these integrals, and we're adding to it n minus 1 of them. So how many would we have total?
N.
N of them, right? Because you're doing n minus 1, add 1, so you'll have n of these. So we have n of these integrals. Is equal to negative sine to the n minus 1 of x cosine x plus n minus 1 integral sine to the n minus 2 of x dx. We're almost there. One more step. All right.
Would it be divide both sides by n?
divide everything by n, divide n, divide n, divide n. And if we do that, one way you could write this is to write it as -1 over n sine to the n minus 1 of x cosine x, and then plus n minus 1 over n integrals of sine to the n minus 2 of x dx. Now we do need to add a plus c because we know this is an antiderivative. Well, no, we don't need to actually, because this will give us a plus c. So we're fine like this. So this is just, there we go. And that's the formula. All right. It is a reduction formula. It takes the power n, creates a new, like it basically starts with the power n, gives you a bunch of crap in a new integral, but your new integral now has that power reduced by 2. So if you do it enough, you'll get it down to where the power goes away. Okay, that's it. We are done with 6.1, integration by parts. I move on. All right, the next section, 6.2. These are the notes. Trigonometric integrals and substitutions. I already told you there's 2 parts to this: trig integrals, trig substitution. Substitution will start when we get to, just so you know, where is it? Trigonometric 6.2.9 is where trigonometric substitution parts. That's the second part of this section. Everything before that is trig integrals. So before we begin, we should all know these things going into this. Antiderivative of sine, right? Negative cosine, shouldn't even take much thinking. Antiderivative of cosine we know is sine. And then we talked about what happens if you have a number in front, right? If there's a number in front, you have to scale that thing out. We talked about that a few classes ago for both sine and cosine, all right? So hold on a second. There we go. All right, so that we should know going in. So what we're doing now is we're going to look at integrals. Right now, we're just going to look at integrals that somehow in the integral have just sines, just cosines, or sines and cosines together. Right? That's what we want to focus on. And so, and then after we do that, we're going to do integrals that have just tangent and just secant. Okay, that's what we're gonna, there's 2 things we're gonna look at within this one section. Sorry, let me say, this section has 2 main parts to it. In this first part, trig integrals, there's 2 things in it. First is sine and cosine stuff, then it's tangent and secant stuff. And then we get to next week. All right, so here's the strategy. There's a strategy for going after integrals that have various powers of sine and cosine. And here are the strategies. There's basically 3 strategies. Okay, the first strategy is to look to see if you have a cosine in there raised to an odd power. If we have cosine to an odd power, we will follow this little procedure right here, which I'm not going to read through it yet. If we have sine to an odd power, then we're going to go and do this procedure. If we have either the sine or the cosine being even, if either of the powers are even, then we have a different procedure. All right. So I don't want to read through the procedures. I want us to do examples and then I'll refer back to the procedure. So let's do our first example. Let's do the integral of sine cubed to 4t dt. I will refer back to this. All right, so what you have to do first is just convince yourself that there's nothing you've learned up to this point to do this. Now, the reduction formula we just used, right? I just created the reduction formula for us, right? We're not allowed to use that because on a test you won't have it. All right. You don't have that reduction formula. So we have to act like all we have is what we've learned up to this point. There's no basic U substitution you can do. And there's even integration by parts won't work. All right. So we have nothing at this point to handle this. But what I do see is an integral with a sine to an odd power. So if I refer to the notes, if we have sine to an odd power, that's this one right here. Well, you know what? This is kind of clunky. I wonder if I have that somewhere else. Yes, if you go to your formula sheets that are allowed on that are on Canvas for you, if you go to your formulas, oh, do I not have it here? What the hell? I know I have it on Canvas. Let me bring it up real quick. Go to our class. I'm so nice to y'all, and y'all don't even know I'm so nice. If you go to your formula sheets, these are all the things you can have on your exams, right? In here, you'll see trigonometric integrals and substitutions. This sheet you are allowed to have on your test. All right. I'm going to open it up as a PDF. This sheet summarizes everything I'm about to go through. So this is how to integrate powers of sine and cosine. We have the 3 different strategies. Right now, what we have is this one. We have sine to an odd power, don't we? Sine to an odd power. So I'm going to copy this strategy down and I'm going to bring it over here to our notes. We're going to finish this problem out. So here's the strategy. If we have sine to an odd power. Okay. I have sine to an odd power. So what I'm going to do first is I'm going to, what they say, save one factor of sine. Okay, what they mean by that is this. You're going to integrate, you're going to take this sine cubed and you're going to peel one of the powers of sine off. Okay, that yellow step is this step right here. Since you had an odd power, right? You had an odd power for the sine. If you peel one of the sines off, what's left will be an even power, right? Because you start with an odd power, you peel one of the sines off. What's left there is even, guaranteed, yes? Guaranteed? Yeah, okay, yeah. So this being an even power of sine, what I can do is use the Pythagorean identity that sine squared x equals 1 minus cosine squared x, which for us in this particular problem, if I'm using that, it would mean sine squared of 4t is equal to 1 minus cosine squared of 4t. You don't understand that? I'm just using the Pythagorean identity for sine squared. I'm going to replace this green part with this in red. So it's going to become integral 1 minus cosine squared 4t. Then I still have sine 4t dt. So the step I just did is this. I used that and I expressed the remaining factors in terms of cosine. So you see, I've got this right here is now in terms of cosine. Yeah. Now it's just a U substitution problem. That's all it is. It's just a U substitution. You make a substitution U is equal to cosine, in this case of 4t. So what I'm trying to get you to see here is that if we let this cosine right there, not the square, just the cosine 4t itself, if we let that be U, do y'all see we have du here? We have something in its derivative. We're off by a sign, but we've got something in its derivative. So it will guarantee go by this basic U sub. So now I'm going to go du equals net. What is the derivative of cosine 4t?
1/4 of cosine 4t.
Careful.
It's 4.
Or, so we're differentiating this time, right? So you take derivative.
Oh,
you're- Yeah. You went the
Yeah.
other way. Right?
I forgot
So
about
if-
the,
The 4 comes out with the chain rule, the negative, because derivative cosine is negative sine. So this is u. U is the cosine 4t. The derivative of that is negative 4 sine 4t dt. We have sine 4t dt right here. We don't have a negative 4, right? We don't have negative 4. So I'm going to scale it. Negative 1/4 du equals sine 4t dt. And now they match, right? This thing here matches with that exactly. See, I haven't called on anyone today. Ricardo, you there? You good? You happy? You following me? I can't hear you. It showed that you were unmuted. It's okay.
I'm using some really
Okay,
ancient
there we
headphones
go.
from the
There you
library.
go. Yeah, I got your chat. Maybe we can talk later.
Okay.
So are you following this? Can you hear me or no?
Say that one more time, sir.
Are you following where I am here on this
I
problem?
am, yes.
Can you tell me what the integral is in terms of u?
So it'd be, so for, let me take a look at this. So the du, it'll be a negative 1/4 on the outside.
Okay. You want the negative 4th out here? And the
The
du in the back?
du is the sine,
Yeah, that's this thing.
and
Okay.
then
What does this become?
that just becomes into,
Replace the cosine 4t with what?
oh, for the u.
With
So
u,
one,
right?
that would be 1 minus u.
1 minus u squared. Don't forget the squared, right?
Yes.
1 minus u squared. And then over here we have just du. And then you pulled the negative 1/4 out. Good. Now we can integrate this, right? We have 2 different terms and we can integrate them just term by term. So we're ready for an antiderivative here, negative 1/4. The antiderivative of 1 would be what?
U or
U, yeah, u. And then minus antiderivative of u squared,
at 1/3 u to the 3.
u to the 3rd, and then that's it, right? Plus c.
Mhm.
And then last step, replace u with what it was, right? And we're done. So cosine to the 4, cosine of 4t, sorry, minus 1/3, and then cosine of 4t, all of that cubed dt. Sorry, dt
Plus
plus
c.
c. Yeah. Good, thank you. Questions? Sine to an odd power. Peel off a sine. Rewrite the other part in terms of cosine. Let u be that cosine piece. Make the substitution, scale if you need to. Rewrite the integral in terms of u. Integrate, that part should be the easy part, and then plug everything back in. That's how you do sine to an odd power. Got
it
it?
seems a lot easier than that formula. Not that the math was easier, but the final result was nicer.
Yeah, you could argue that this was a little bit easier than using the reduction. Let's try another one of these.
Can you show me just something really quick on that one? Maybe I'm like spacing out. On the negative 1/4 u minus 1/3 u cubed. Where did we get the u from?
Right here, we did the antiderivative of 1,
Oh, okay, got
right?
it.
But because we're doing it with respect to u, the antiderivative would be u, not x.
Yeah.
So
got
this
it.
would be u and then power rule, right?
Yeah, got it.
So let me do another one, okay? What if we had this? You're not gonna like this. You're gonna like it. You're not gonna like it. sine to the 7th x dx. I'll keep it nice. Just gonna put x in there. I have an odd power, right? So first thing I'm gonna do is I'm gonna peel off one of the signs. Because I'm allowed to, right? And when I do that, I'm guaranteed that what's left, this sine to the 6x, I'm guaranteed that it's to an even power because I peeled one sign off, right? It was odd, I peeled one off, I'm gonna have even. The problem is that our Pythagorean identity says this. It says sine squared x equals 1 minus cosine squared x. Y'all know where that's coming from, right? That formula right there. Y'all know that's just Pythagorean identity, move things around. Yeah. Okay, so we don't have sine squared, right? We have sine to the 6th. So is this true? Does the Pythagorean identity work? Just can we replace that with a 6 and it still be good? What do you think? Or does it have to be squares?
I think it works, doesn't it?
Is it a
Okay,
3? I
right.
thought it was a 3 minus. No.
It has to be squares. That's
Has
the
to be
only way
squares.
the Pythagorean identity works. And it comes from the idea that you have to remember where the Pythagorean identity comes from. It comes from the idea that if you have a unit circle and you go to some point here, then if this is theta, yeah, let's make it theta. The x coordinates cosine theta, the y coordinates sine theta. And if you look at it like a triangle, this is sine theta, this is cosine theta, and then this hypotenuse is 1. And so the Pythagorean, a squared plus b squared is c squared would tell you cosine squared theta plus sine squared theta equals 1 squared, which is 1, and that's your identity. But you're not allowed to make those 4th powers or 6th powers or 8th powers. It only works when you do a squared plus b squared is c squared. So it has to be squares. All right. So that's not
Could
going to
break
work.
it down even more.
So
Pardon?
couldn't we just break it down into sine squared 3 times and then do it 3 times and then multiply those back together?
Yeah, we could. And
Yeah.
that's what we're going to do. And it's not going to be pretty, but that's what we're going to do. Okay. So I'm going to do it a little different. Instead of looking at sine to the 6th power of x as sine to the 6th, I'm going to look at it as sine squared x cubed. You could do sine squared times sine squared times sine squared, but I think it's just more condensed to write it sine squared to the 3rd power. Do y'all see that that's still sine to the 6th? And now I'm going to do the replacement of the inside with 1 minus cosine squared x. Then to the 3rd, then sine x dx. Now my U substitution. U is equal to cosine x. Du is equal to negative sine x dx. I have a sine x dx. I don't have a negative, so I have to multiply both sides by -1. So negative du is sine x dx. So I'm gonna start matching things up. This here is this, and then my cosine x is my u. Caitlin, what do we have? Are you following, Caitlin? I know I'm moving fast here.
Yep, I'm just going through it all.
Okay,
Let's see. So we would have here 1 minus u to the power of 2
yeah.
uh,
All of that, right?
times negative du.
Negative du. So
And
yeah,
the
I'll-
negative can be moved out.
yeah, negative outside now. Maybe I didn't hear you. Did you?
Oh,
say-
yeah.
Okay, the 3rd power has to be
Yeah.
here, right? The
Yeah.
3rd power has to be there. Okay. Shoot, well, how do we do this? We can't do what we did just a minute ago. We can't do the antiderivative of each one of those because it's cubed. And you're not allowed to just cube each one because then you're gonna burn in algebra hell for that. You got to expand this, right? You got to actually multiply that out. That's the way we're gonna do it. We're gonna take 1 minus u squared times 1 minus u squared times 1 minus u squared, and we're gonna like expand all that out. It's algebra, but it's not terrible algebra. It's not fun algebra, but it's doable. So here's the way I would do it. So I would do 1 minus u squared. Is there a question?
Yeah, just out of curiosity, why couldn't you use the inside of the cubic?
Why couldn't I what?
Why would you not be able to use maybe 1 minus u squared?
Oh, okay. Like make a u sub on this inside piece,
Right.
because the derivative of that would be 2u, negative 2u. And I don't have a negative 2u anywhere out here. So I think I'd run into an issue that the substitution wouldn't work.
Okay, I see what you're saying.
Yeah, because you would have to pick the u squared. And so the derivative would have a u in it, which I don't see anywhere.
Yeah, because use kind of like you do use of it. It's kind of like a reverse chain rule, right? I guess.
Yeah, exactly.
Okay,
So
I
you'd have
see
that
the problem.
derivative out there somewhere.
Okay.
So I'm just expanding this out over here. Just, what I did is I decided to FOIL this one out and collected like terms. And now I'm going to do another multiplication here, 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 and then here, here, here. And I should get 1 minus 2u squared plus u to the 4th minus u squared plus u to the 4th minus u to the 6th. I think I did all that right. 1 minus 3u squared plus, I feel like I'm missing a 2. I am. Right there. What? Missing a 2 right here, I believe. Minus u squared plus 2u to the 4th minus u to the 6th. Okay, yeah, I was missing it there. 3u to the 4th minus u to the 6th. Questions on that algebra? So now my new integral is minus, and then now I can do the antiderivative of each of these. Okay, you know how to handle it from here? Yeah, you just do power rule on each of those. Don't forget to replace u with cosine. Plus c, you're done. I need to proceed. ... You finish that one yourself. All right, let's look at another one. Another example. How about this one? I'm going to bring up that page again where it had the, where is it? Where is it? Did I close it? Oh no, it probably brought it up in the browser. I hate that. Okay, so here it is. First step, we look to see if cosine is odd. If cosine's odd, we do the first thing. If sine is odd, we do the second thing. If the sine and cosine are even, we do something else. So for this one, I have cosine odd, don't I? See, I'm ignoring that sine is even, because the first step in that thing was check if the power of cosine is odd, which it is. So if it's odd, I'm going to do this set of steps. And you're going to see it's very similar to what we just did. Very, very similar. We're going to do the exact same thing with that peeling off, but this time we're peeling off one of the factors of cosine because the cosine was odd. So I'm going to peel off that factor of cosine. So this becomes integral sine squared x cosine to the 4th x cosine x dx. This cosine x dx is going to be my derivative of my substitution. I'm going to be making a substitution that u is sine x. And then that'll be its derivative right there. But I've got to get everything here in terms of sine. So the Pythagorean identity I'm using this time is the cosine squared x is 1 minus sine squared x. So I'll do this. Sine squared x. Rewrite cosine to the fourth is cosine squared x squared cosine x dx. So because I wanted to use Pythagorean identity, which involves cosine squared, and I had cosine to the fourth, I have to rewrite the cosine to the fourth as cosine squared squared. This will become sine squared x, parentheses 1 minus sine squared x squared cosine x dx. Do you all see that that cosine we pulled out? That's my du, right? My substitution that I'm going to make is u is sine x, right? So that cosine x dx, I'm really kind of ignoring it, and I'm making sure that everything over here has signs in it. Once everything over there has a sign in it, I can replace those things with u's, and my du is going to be sitting right here on the side. So du, fortunately for us, the derivative of sine is just cosine. So I don't have to scale. There's no negatives to worry about. Everything's beautiful. And I can rewrite the integral. This one would be u squared 1 minus u squared squared du. U is sine x, u squared 1 minus u squared, all of that squared. I'm going to have to expand this out. 1 minus u squared, I'm going to need to square it, right? I need to go over here, 1 minus u squared and square it. And that will give me 1 minus 2u squared plus u to the fourth. And then when I distribute that u squared through, so what I get over here goes in for this, and then that u squared has to go through it, right? Which is how I got this last line. Dot, dot, dot. You can finish that now? Yes? Power rule. Just remember at the end to plug your sine x back in for u.
So all you're doing is manipulating it. So you have the derivative and then you sub to hit that other side and then just clean it up after that.
Mm-hmm. Yeah. It's taking advantage of the fact that sine and cosine are very intimately connected to one another through their derivatives. And by peeling one off, it can become the derivative of the other one. So you've got to get the rest of the integral in terms of the, you know, the opposite of whatever the thing you peel off is. Let me give you all one. This one is kind of not a trick question, but you don't want to get yourself like going too crazy with this. So when you look at this problem, right, you say, oh, I see sines and cosines in here, right? So then you start going, oh, I'm gonna go and start looking at this, right? Let me go see which of these cases is it, right? No, because this is just basic U sub. Right here off the bat. Okay, if you let u be sine x right now, du is cosine x. And so this integral becomes, if you cosine x dx, right, that's my du. And then this right here is my u. These two are my du. And so this just becomes u to the fifth du, which is 1/6 u to the sixth plus some constant, which is going to be 1/6 sine to the sixth of x plus c. I went through that quickly, but the point of it is you don't want to become like a robot where you're like, I see sines and cosines, I go to sheet tells me do this. You always want to be looking at it from the perspective of what we've already learned. Like, okay, so these problems that I'm doing, as I'm doing them, I want you to understand that I'm already, when I'm starting the problem, I'm already at a point where I've eliminated all the other things we know. Okay, that I've taken that into account. This won't go through U substitution. This won't go through integration by parts. And now I'm here. This problem doesn't need all. I mean, just go U sub, you're done. That kind of makes sense? What I'm trying to get you to kind of think a certain way, I guess.
So I have a quick question.
Yeah.
Could you have done this the other way?
Well,
Like, would it have even worked?
if you peel off, you would peel off a sine, right? And then if you peel off a sine, then you've got to get the sine to the fourth that's left as a cosine. So it'd become 1 minus cosine squared, all of that squared. And then you could do it, yes. So
Yeah.
it would, but it would probably take you a lot more time and it would be a lot more places to make mistakes.
Okay.
All right, let's look at another one. Okay, you know what? We're not ready for this one yet. I'm going to put it here and I'm going to do another one before I do this one. Let's do this. Let's do integral cosine squared x dx. Something very, very basic. Right, so you start running through your ideas, right? Like, oh, can I do this with anything I know? Integration by parts. You start messing with things and it's not going to happen. Okay, so you say, oh, okay, well, I've got, you know, trig integral. And according to the trig integral stuff, I look and the third step says here that if I have any even powers of sine or cosine, then I can start using these identities from pre-cal. Not the Pythagorean identity, some other identities. So I have an even power, right? I have an even power, right? I've got an even power of cosine. And so what I'm going to do is I'm going to use this formula from pre-cal that allows me to take cosine squared and rewrite it as this. That is known in pre-cal as, there's two ways it's referred to. It's referred to as the half angle identity, or I prefer to call it the power reducing formula or the power reducing identity. Because what it does is it's like a give and a take. You have a way of taking cosine and no longer having it squared. It's not going to be squared anymore. But the give and the take is that you're going to have to double the angle. So whatever angle was in here has to be doubled when you use this formula. So since the angle in here was x, in the formula it's twice that. So let's do it. I'm going to just take this and rewrite cosine squared x as 1/2 1 plus cosine 2x and then dx. The 1/2 is a constant, it can come out. And now I just have two terms. And since I have two terms, I can do the antiderivative on each one. Miyaki, how's it going?
Good.
No, I saw your cat and I was like,
Yeah, he's just
he or she?
going crazy. It's the he. He's just going crazy while I'm doing Zoom
He
right
just
now.
enjoys, I think he enjoys calculus too, quite a bit. I can just tell by the look. Okay. All right, that's
Thank
all.
you.
I just wanted to say hello to your cat.
Oh,
And to you.
yes, hi too.
Okay, so these should go pretty easy. Let's see, 1/2 antiderivative 1 is just x. And then this one, you have to be careful because we have a 2 inside, right? So the antiderivative cosine is sine,
1/2.
but we've got to
sine.
do half. Yeah, half out front, right? Sine 2x like that. Then we do plus c. Come on, questions. All right. All right. Let's try this one. Cosine to the fourth. Cosine to the fourth. I'm going to copy this and bring it over here. So we do have cosine to an even power, right? We have cosine to the even power. So I can use this. I'm allowed to use this, but this formula only works for squared. Okay, you cannot do this and just say, oh, change that to a 4 and change that to a 4. No, that's not the way it works. All right. It only works with a squared. So unfortunately for us, when we do this, we're gonna have to rewrite this as cosine squared. Now that's a beta t. So beta for us in this problem, beta is some constant. We don't know what it is. All right. But it's a constant. It's a number that's fixed. So I'm going to take that and then I'm going to square it, dt. Then I'm going to use the formula to replace what's in parentheses with 1/2, 1 plus cosine of what?
Two BT.
2 beta t, right? Because the original cosine squared beta t, the beta is like the x, so we're going to double that. So we're going to have 2 beta t. So we're going to have 2 beta t. And then that's it, right? That, the 1/2 goes through that parentheses. All of this still needs to be squared, dt. Right, so the cosine squared beta t turned into this stuff here, which came from that formula there. We gotta keep going. See, there's no, with this, there's no like the previous problems where we had like the sine or cosine on the outside where we did a basic U substitution. We don't have that here. We have nothing on the outside that we peeled off. So I have to algebraically continue to grind this out. Please notice that there is a multiplication right here. And since we're squaring the whole thing, I can square the 1/2 and square this parentheses in blue. I can do this. Integral, square the 1/2, get a 4th. Take the 1 plus cosine of 2 beta t, take that thing right there and square it dt. Now I'm gonna do something that you don't want to do, but you're gonna have to do for this problem. You're gonna have to take 1 plus cosine of 2 beta t and square it, multiply it times itself. We have to expand this. And like I said, you're not gonna like it. So 1 times 1, it's 1, yay, okay. And then this times this, and then this times this. Those are the same thing. So we get plus 2 cosine of the 2 beta t's. And the last multiplication is the one that's gonna mess us up. It's gonna make our lives bad. We have a cosine 2 beta t times cosine 2 beta t, which is gonna give you cosine squared of 2 beta t. All right, I'm gonna rewrite. So 1/4 is a constant that's coming out of the whole thing. Everything that was here squared, we just simplified that, and it now became 1 plus 2 cosine of 2 beta t, but then plus cosine squared of 2 beta t, all of that dt. Did anyone see where I'm going here? Where I'm about to go? Can
Are
you
you gonna
tell me can you tell me the antiderivative of this?
It's t.
T, right? So that's good. We got that. Can you tell me the antiderivative of that? It's just a cosine, right? So you should be able to find the antiderivative. You're gonna have to scale things, but that should be doable. But what about
Yeah,
this one?
easy.
What about that one?
You have to
You
do
gotta
what?
use that same formula
I
again.
have to use the formula again, and I have to power reduce that one again before I can do anything with it. So I'm gonna do that. Yeah, this is no fun. Look at cosine to even powers, sine to even powers are a pain in the ass. All right, they just are. Because you got to keep on using this power reducing formula, and it just gets really algebraically long. Okay,
Only thing though is if the reduction, or not, maybe not the reduction, but if you use the formula and you get the answer for whatever the formula provides, you should be able to plug it in as a result. For you shouldn't have to do the algebra too many times if you do the algebra on cosine squared 2 beta t. Do you see what I'm saying?
I'm not
You've
sure.
already done it once.
Saying I don't have to do
Because-
the algebra.
I'm guessing it's because he already went through the process once. He's saying that since we already have the information, we could just plug it in.
You just plug it in. Yeah, exactly.
Like plug in what we've already done into the next cosine squared 2 beta t. Does that make sense?
You've already factored cosine squared beta or 2 beta t, and you write that off to the side somewhere. Then anytime it presents itself, you should be able to plug in whatever your result is.
Hold on though. On this formula, whatever the angle is, it gets doubled, right?
Mm-hmm.
So if I power reduce this, I have to double its angle, which means it's 4 beta t this time, not
Okay,
2.
I see.
You see? So when I do
Yeah.
this next step, I'm going to get something different than what I had before.
Okay, I guess
Yeah,
we'll just
let
see
me
what happens.
continue. Let me continue and let's see what it becomes. 1 plus
Okay.
2 cosine of 2 beta t plus, now this I'm about to do the power reducing half angle, whatever you want to call it, on that. So that becomes 1/2, right? I'm using this formula right here. 1/2 parenthesis 1 plus cosine, right? Now I can kill the power off, but I've got to double the angle. So I double 2 beta t, which becomes 4 beta t. There. That's that part. All of that dt. Still going. Haven't done the antiderivative yet. 1 plus 2 cosine of 2 beta t plus 1/2 of cosine of 4 beta t, all of that dt. Just distributed the half through. This fun? These are brutal.
Very
Okay,
fun.
I'm gonna do 1 1/2, 1 plus 1/2, that's 3 halves. I'm gonna put those together, so I get 3 halves plus 2 cosine of 2 beta t plus 1/2 of cosine, cosine of 4 beta t. I'm just making sure I'm keeping track of all my parentheses there. I think we're finally to a point where we can take an antiderivative. We have chipped away at this, right? We started out with cosine to the 4th. We wrote it as cosine squared squared. We used the power reducing formula, but it was still squared, so we had to expand it. When we expanded it, we got another squared, but this time 2 beta t. Then we had to use the power reducing again, and that became now a cosine 4 beta t, but you don't have any more squareds. Distribute, clean it up, and now let's do antiderivative. So 1/4 out front, antiderivative of each one of these. So this is 3 halves t. That's the antiderivative of this. The antiderivative of this, cosine of 2 beta t, I have the 2 that comes for the ride. the antiderivative of cosine is sine, right? But I have to scale because I've got some stuff in here. What do I scale this by?
1
1
half.
over what?
1/2 beta.
1 over 2 beta. Good, 1 over 2
Mm.
beta. And then sine of 2 beta t, because beta is a constant. So we're having to scale by 1 over 2 beta. Then we still have over here plus 1/2 times now the antiderivative cosine of 4 beta t is sine 4 beta t, but I have to scale by 1 over 4 beta this time. Sine of 4 beta t. All of that plus c. Are we having fun yet?
We have to distribute that 1/4 out because
I'm
that'll.
going to right now. You
Okay.
wouldn't have to on the test, but I'm going to.
Okay.
Here to here, 3/8 t. Here the two's canceled. And so that 1/4 hits the 1 over beta. I get 1 over 4 beta sine of 2 beta t. And then, let's see, I've done that here to here. Okay, that was already 1 over 8 beta. What's this? I can't do math. 32. So plus 1 over 32 beta. Yeah. Sine of 4 beta t plus c. There it is. I think. Yikes, huh?
Yikes.
Imagine cosine to the 6th power.
I
Because
don't want to imagine that.
it's in your homework.
Oh, God.
It's in your homework. So
That'll be
it's
fun.
and like I said, I've said this before, like I'm the messenger here. The homework problems are what the author thinks you should do and what I think you should do. Every student should have to suffer through cosine to the 6th. You're probably gonna have to turn your page sideways. That's how long it's gonna be. But every Cal 2 student should have to endure that because you have to keep track of all this stuff. It's really messy. Okay.
That's what this is like, doing it all full on double pages for.
Yeah. Let's do this. Let's go to Wolfram Alpha. I'm curious what will happen if I say integrate cosine. I don't even know if it's going to take, I'm going to do a times x instead of beta t, and then I'm going to say raised to the 6th. I'm just curious what it's going to do. I don't even know how it handles the a. Oh, it did it. Wait a minute, it just changed the answer. Okay, so there it is, right? This is what it got. And this is not going to look like our answer. And that's because the computer used some other identities. And they've got like, you know, a 2 beta, remember the A is like a beta. So they've got like a 2 beta x inside of a sine and a 4 beta x and a 6 beta x. We didn't have that. We had just a 2 beta and a 4 beta. They did some stuff. They did some stuff that I don't know, but our answers are the same. They just don't look the same, which is
Could you
why.
compare them in Desmos?
What's that?
Could you compare the two in Desmos?
You could, yeah, you could graph them. But see,
wasn't-
there's a constant in here, so that'd be a little bit.
Wasn't ours to the 4th though?
Oh, or ours was to the
Yeah.
4th. You're right. You're
Yeah,
right.
ours is to
Sorry,
the 4th.
sorry. Okay, no,
It
no.
would
no.
it would look the same on top, I think.
Yeah, I'm curious.
Similar.
I'm curious whether or not. Yeah, I guess. Okay, so it didn't use any other identities. 12 over 32 is what?
I'm guessing the 3/8.
Yes, the 3/8, right? 4 goes into both of those. So 4 goes in 12 3 times, goes into there 8 times. Put the ax over a, that the a's cancel, you just get the x. So we had 3/8 x, right? Or 3/8 t. And then they have what, 8 over 32 is 1/4. So 1 over 4 beta, sine of 2 beta t. Is that what we have?
Yes, sir.
And then the last one is 1/32 beta sine of 4 beta t.
So what is that 3D plot there?
Actually, I'm
Because
not
that is
sure.
a very terrifying picture.
Yeah, no, they are. What are they plotting? Hold on. Are they plotting the result? I'm not sure what they're plotting on this, actually. See, this would have to be some sort of function of two variables. So I think what they're doing,
They might be assuming A is a variable.
I think it's assuming A is a variable. Well, let me see. Hold on. Yeah, it does. See on this axis, it's the A axis and then the X axis. So it's assuming that this is a function of two variables and it's plotting it as a surface.
Okay,
Yeah, which is really weird that it would do that. But
yeah.
it does weird things. As you can see, it does a lot of other things too. All right, so I'm also curious what would happen on Symbolab. Let's see, we integrate. Let's see, cosine. Oh, I'll put b times x on this one. Raised to the 4th. See if I get that right this time. Usually, yeah, see, usually what happens on these is they do some, oh, what the hell? Yeah, this, can y'all see this? See that? Cosine beta x, right, to the 4th. This is the answer. Right. No human's getting that answer. All right. No human is getting this answer. This is a computer and they used all sorts of identities that a human wouldn't use. They did a U substitution. What? Simplify. Integration by parts. This is when I know a student's cheating on Symbolab. I mean, it's just so obvious because they do things that just aren't anywhere within the realm of what a human would do. It's only the way a computer algorithm works. All right, so here's where we are. We got 8 minutes left. We are done with the first half of the first half. So we're a quarter through. We still need to talk about what happens when you have tangents and secants in an integral. All right, which we'll have to do next class. So what I would say is for homework, make sure you've done everything in 6.1. In terms of 6.2, you don't have to complete the whole thing. Just do for 6.2. Let's see. Let me see what's on our assignments first. One through 61. So yeah, number 10 is cosine to the 6th. The first 16 problems. The first 16 problems can all be done using either something you've already learned in a previous section, U substitution, integration by parts, or what we've done today where you have sine and cosine, even, odd, and you pull things out. Remember that if you're given like cotangent, remember cotangent is cosine over sine, right? So yeah. Yeah, we have, I think we're good. Do y'all have any questions?
Do you want us to turn in 1 through 16 on Sunday?
Yeah, so like I would say you don't need to do all of them, okay, because it's Super Bowl Sunday, but I would say that would be a good exercise set for you to try them all. You might get hung up on a few of those, but 1 through 16 I think is a good good for what we did today, and then it's going to take us a while before we get this section done. And we're going to probably get into midway of next week. But 1 through 16 sounds like a fair game. Turn in what you can. Super Bowl Sunday, I wouldn't expect that you're working Sunday night instead of, watching the game, but plan your life accordingly, right? Get it done early.
So we're turning in the second part for 6.1 and then also the 1 through 16 on 6.2.
That's right. The second part for
Gotcha.
6.1 and then the first 16 problems of 6.2.
Gotcha. And what is the second part? Because the first part was 1 through 7. So I'm guessing it's everything after 7 through.
Right here. Sorry, it's right there. So it would be this stuff right in here.
Gotcha.
And again, remember, this is all about doing these things until you feel comfortable, right? And I've told you also in Cal 2, there's no such thing as doing too many. I'm not going to sit here and go through all your homework and look at each thing and, but I do expect you to turn something into me.
Yeah, just the overlap of the 1 through 7 is also
Yes.
overlapping with so I just want to make sure I'm doing enough to because I can do a lot of them.
Okay.
It's just I wanted to see just how much I can take off because since I already did them in the previous week, 1 through
Yeah,
7.
you don't have to redo them. If you did the
Yeah.
first 7, of course, just do, from there on.
Okay, yeah, that's what I was curious about. Thank you.
Yeah. Anything else? I still have 4 minutes. You're welcome to go. I don't think we did this though. Did we do this? This is like a simple integral that I don't think we've even talked about. What's the antiderivative of tangent x? Not the derivative, the antiderivative. We haven't done that, right? It's on your formula sheet though. It is on your formula sheet, but let me just show you how it's done real quick. It's not hard. You just rewrite this as sine x over cosine x. That's what tangent is, right? And now you do a basic U sub. Let U be cosine x. Because the derivative of that is negative sine x. And it's in the numerator, right? It's up top. So if I multiply by negative du, or multiply by -1, I get sine x dx. So I guess what I'm trying to get you to see is this could have been rewritten as 1 over cosine x times sine x dx. And then I can make that substitution. Follow it? This now becomes integral, the 1 over cosine becomes 1 over u. And the sine x dx becomes negative du. So I'll put a negative, just, I'll put it outside. Negative du.
So it's the integral of the tangent and natural log.
It's natural log. Yep. So this becomes equal to negative, and the antiderivative of 1 over u is natural log of the absolute value of u plus c. And now we replace that replace the u with what it was, which was cosine, I believe, plus c. So the antiderivative tangent is negative natural log of cosine of x. See, it was just a U sub, right? That's all it was. Now, if you go look at your formula sheets and you go to where the antiderivatives are, we just did number 12. Most of these can be done that way. Cotangent, secant, most of them can be done that. Well, secant can't. I have to show you secant. I'll show it to you next time. It's on the notes. Wait a minute, is that what we got? We didn't get that, did we? We didn't get that.
We got negative natural log of cosine.
Yeah, did we mess up? We as if I'm blaming it on you. We did not mess up. Because we have this property that when you have natural log of x to the n, this is equal to n times natural log of x. Property of exponents from college algebra, right? So if you have a number, a power on x inside of a natural log, you can pull it out. But that means if there's a number on the outside, you can push it up. So I'm going to take that -1, I'm going to push it up as a power on that cosine. So it becomes cosine of x to the -1, which is not the inverse cosine. That's not what that -1 means. It means 1 over the cosine,
Which is secant.
which is secant. So we got the same answer. Just doesn't look like we did. Yeah, that whole thing here, this whole cosine -1x versus, you know, cosine x to -1. This is just, I wish in math we had a better notation for the inverse, because it's too easy to confuse it with the reciprocal.
I mean, there's arcs. You can call it arc
You
cosine.
can do arc. Arc is really a good way to kind of avoid that trouble.
Yeah, I always I write it usually as the -1 because that's easier to write, but I almost always call it an arc cosine.
Yeah,
Because
well,
then
yeah.
there's no differentiation in my mind, at least.
I mean, we could have done something very simple, you know, we could have done like put that in parentheses, or, you know, you could have said, put a little line under it or circle it, something to distinguish it from the other thing, but we didn't. All right, everyone, 12:41. Y'all have a great one.
You too, sir. Thank you.
Bye.
Okay.
Have a good weekend, sir.
Yep.
Thank
You
you.
as well.